Hello, Riles. Let's take a look at a couple of other examples from lesson 1.2 on point slope form, standard form, and then alternative methods of factoring. So let's try another find an equation of a line example. Let's find the equation of a line perpendicular to. You know what? Let's introduce a new term here that we're going to use in our course, or normal to. Y equals negative 2/3 x plus 5. That is passing through. The 0.6 negative 1, and let's do this in standard form. And I really want you to practice getting equations in standard form. It is important for the vectors portion of our course, and we'll find other uses for it later as well. Okay, so the word normal is synonymous to perpendicular. If you have in physics, some people might be able to tell you about a normal force that's being applied it's like a reaction force in a reaction to gravity, perpendicular from a surface kind of thing, or normal to the surface. So I will start with a rough sketch here just to visualize things a little bit, not really to try to figure out what the answer is. If I've got a y-intercept of 5 and a slope of negative 2/3, notice I'm using my slope as a ratio. I'm not counting down 2 squares and over 3 squares. I'm saying that I'm going to run about 50% more than I'm rising, or falling, rather. The line that I'm looking for is going through, well, I don't actually know exactly where the point is. If this is 5 and that's 5, I guess 6 negative 1 would be about here. So it should look something like that. This is really only useful, though, if I'm going to try to find the equation of this line that I'm looking for in y equals mx plus b form, so that I can sort of check my y-intercept. It will remind me of the relationship between slopes of normal or perpendicular lines, though. So let's start this off by saying the slope of the first line that we're given is negative 2/3. That means that the slope of the line that we're looking for, and I'm differentiating between the two lines here, I suppose, is going to be 3/2, the opposite reciprocal of negative 2/3. And now here is the advantage of point slope form. You don't need to write out y equals mx plus b, substitute in the slope, substitute in a point, rearrange, find b, rewrite it in the format y equals mx plus b. In fact, if we were just asked to find an equation of this line, I would say y minus y1 is going to be equal to m times x minus x1. That's an equation of this line. And for the similarities between this and the vertex form of our line that we'll see in our, the vector form of a line that we'll see in vectors, is this is basically showing you some point on the line. Notice the reversal of your transformations. There's a horizontal shift right 6, a vertical shift down 1. But that occurs, of course, after a vertical stretch by 3/2. So you take your parent line, stretch it vertically by 3/2, then translate it right 6, down 1, and there's your line, like that. Well, now we are asked to write this in standard form, and to review, standard form is capital AX plus capital BY plus capital C equals 0. Has to be in this order. X term first, Y term next, constant term, then an equal sign, then 0. Not 0 equals. It's a different equation. Okay. Your first visible coefficient should be positive. Okay. In the event that A is 0, then B should be positive, kind of thing. You won't find A and B to both be 0, because then you don't have a line. Your coefficients should be integers, if at all possible, and that is possible in our course. And the greatest common factor of A, B, and C should be 1, meaning that it's reduced. So problem number 1 that I see is a fractional coefficient. I'm going to multiply both sides by 2 here. Notice I'm using the distributive property of multiplication through sums on the left-hand side, and I'm not using the distributive property of multiplication through products, because that's not a thing. I multiply the right-hand side by 2, and that 2 is going to divide this 2 out. I don't need to multiply x minus 6 by 2. I'll use the distributive property of multiplication through additions or subtractions on the right-hand side. 2y plus 2 is going to be equal to 3x minus 18. I might have been able to multiply by 2 and distribute in one step, but might have been harder for my reader to follow. Now I'm going to subtract 2y from both sides and subtract 2 from both sides, and then also exchange my left side and my right side. And this is where we still find some really old and terrible habits where students say, I thought if you moved the 3x to the other side, it had to switch sign. And that's absolutely false. If you have 6 equals x, you don't need to write negative x equals negative 6. You're allowed to just change the order of your sentence. If 6 is the value of x, then x has a value of 6. The sentences are equivalent to each other. Okay. I have my terms in alphabetic order, the x term first, then the y term, then the constant term. My right-hand side is equal to 0. My coefficients are integers, and the greatest common factor of 3, 2, and 20 is 1. See, if I multiplied by, I don't know, 4 here, I would have ended up with 6x minus 4y minus 40 equals 0, and that can be reduced. So it should be reduced. You will be asked to use standard form, so make sure you are clear on what it is. Okay. And the other example that I want to try is another curve sketch, but showing an alternative to the factor theorem as far as factoring goes. Let's sketch f of x equals x cubed minus 2x squared minus 4x plus 8. Let's label all intercepts. So the argument here is that your factor theorem really should be one of your last resorts. Some students really attach to it after advanced functions, and they find it useful. It's algorithmic, so maybe there's less thinking involved. It might be easier to program, but it's not the most efficient approach. Instead, if you try all of your other factoring methods, then you should find faster approaches. And one approach that I teach in my advanced functions class is factoring by grouping for common factors. And it's worth trying. It doesn't take long to look at and see if it will work. Notice that there's no common factor. There's no factor common to all 4 terms. I should definitely be trying common factoring first. But I might notice that these 2 terms have a relatively large common factor of x squared, and then these 2 terms have a relatively large common factor of negative 4. That's not so much what's interesting. What's interesting is when I try factoring in groups. Factoring in groups is something you need to be really careful about because it generally does not get me to a factored form. Right? Like me writing it like this is not a factored form. It's still written as a subtraction, but it might help me go towards a factored form. So I partially factor here. I remove the greatest common factor between these first 2 terms, giving me x squared times x minus 2. I partially factor here. I remove the greatest common factor between these 2 terms, and following my the generalized formatting advice of removing leading negatives. We shouldn't leave leading negatives buried inside the brackets. And then this I wasn't trying to force to happen. If this doesn't happen, then maybe I can't group for common factors. But the fact that it has occurred means that I have another common factor of x minus 2. Now, students that are taught how to factor by decomposition might feel like this is familiar, but the other problem with students that were taught that is sometimes they just write this in one bracket and this in one bracket without understanding what they're doing. There's 2 ways I think of sort of visualizing, 2 ways that I can think of visualizing this. I prefer the way of seeing that x minus 2 is a common factor. We remove it as a common factor. X minus 2 times what gives me x squared times x minus 2? X squared. X minus 2 times what gives me negative 4 times x minus 2? Negative 4. Again, I'm saying it kind of sarcastically because when I ask myself the question in English, I hear my own answer. And I can check by distribution by just imagining distributing the quantity x minus 2. X minus 2 times x squared would be x squared times x minus 2. X minus 2 times negative 4 would be negative 4 times x minus 2. So not a lot of people distribute like this. Most people will do first outside, inside, last kind of thing. Almost said FOIL there. The other way of visualizing this is viewing it as like terms. That if you have x squared, x minus 2's, and you subtract 4 x minus 2's, then you will have x squared minus 4 x minus 2's. But I don't like this approach because I find a lot of students, or a group of students from specific teachers, they just memorize how to do this. They just say you put this and this in one bracket and then you put that in another bracket, and then they get confused about why there's not a squared on there. So I prefer common factoring, common factoring, common factoring. And then, of course, I always want to factor completely. So I'll notice that there is a difference of squares here. I'll factor that as a difference of squares. And then for the purposes of sketching, you might find it, I can't really force you to write this expression as x minus 2 all squared times x plus 2. But you're pretty much going to want to. So that when you identify your intercepts, you can see that you only have two different x-intercepts. I don't like saying there's 3 x-intercepts here, but 2 of them are identical. I would prefer that we think about having a linear root at -2 and a quadratic root at +2. I have a positive leading coefficient, so I know that my end behavior is right positive. As x grows, y is going to grow for sure. Because of the odd exponent, I know I'm going to have opposite end behavior. Or I zoom out far enough, it'll look like I have odd symmetry. I suppose I could also use my y-intercept here to check my behavior. I'm pretty sure I'm going through this route, crossing the y-axis above the x-axis, bouncing off of the axis there and coming up. I just want to stress f of 0, you shouldn't be reading your y-intercept off of standard form. If I give you this function and asked you to find the y-intercept, I am severely concerned, let's say, when students expand to standard form so that they can read off the y-intercept. The y-intercept is f of 0. That's its definition. And it's easy enough to get here, I suppose, or to double check it here. It should be, the square of -2 times 2, the double of the square of -2, which is +8. One more time, though, let's talk about appropriate curvature versus preciseness of your graph, or even like using a square scale. You do not want to count out, this is -1, -2, and then this is 1, 2, 3, 4, 5, 6, 7, 8, and draw 8 up there. Okay, draw a smooth curve first. That demonstrates appropriate curvature. And the one problem that I usually have is, for some reason, my eye is drawn to the y-intercept, and I feel like when I draw my curve almost will always look like it's turning at the on the y-intercept. We'll figure out in this course that this curve has to turn sooner, I believe, to be able to come down here. Just don't force it to happen. It might have actually been better if maybe I didn't even draw my y-axis first. Okay, if you draw a smooth curve, in order to come in at the x-intercept of 2 and bounce off, you'll notice that you sort of need to turn sooner than halfway between -2 and 2. Again, our calculus skills will tell us exactly when a relationship turns. But this feels a lot better to me. I draw my curve first, then I draw my y-axis. And then wherever my curve crosses my y-axis, I label that as my y-intercept. I should be making this curvier. I want to demonstrate appropriate curvature. This should be getting steeper. So I think what I'm going to do is grab a pencil, do that in pencil, erase there. I curve more or draw less. And there we go. There's my labeled sketch of the function f. Okay.